Welcome back to the deep dive. So if you've been keeping a close eye on how large language models reason, especially with chain of thought, the engine behind models like DeepSeek R1 or what we expect from systems like OpenAI's O1, then you're probably familiar with this central tension.
Right. Hadoop is, well, it's incredibly powerful for tackling complex tasks, algorithmic stuff, but it's also fundamentally brittle.
Exactly.
Yeah.
One tiny slip up, one calculation error, and the whole chain can just go off the rails. It becomes unreliable or just plain wrong. And we're really past the stage of just saying, oh, the LLM got it wrong.
Uh-huh. The real challenge now is diagnosis. We need to figure out precisely why the computation itself failed, what broke inside the model.
So that's our mission for this deep dive. We're going to take a really close technical look at a pretty radical new approach. It's detailed in a paper focused on verifying chain of thought reasoning via its computational graph.
And it really is a potential paradigm shift. It moves LLM verification away from just detecting that an error happened.
Like spotting the crash.
Yeah, exactly. Towards diagnosing why it happened. It's about tracing the, let's say, corrupted line of code within the model's reasoning process. We're essentially looking at the structural integrity of the model's execution trace to find the weak points.
Okay, so before we get into the weeds of this new white box method, maybe set the scene. What's the current verification landscape look like?
Sure. So traditionally, you can think about verification methods based on how much access they have to the model's internals. On one end, you've got black box methods.
The simplest ones.
Right. They only look at the final output, maybe the probability of the chosen token, the perplexity, entropy scores, things like that. Max prob is a common one.
So it's like checking if the model seems unsure, but you don't know why.
Exactly. It gives you very little internal insight. It just tells you something might be off based on the output distribution.
Okay, and then there are gray box methods.
Yeah, moving along the spectrum, you get gray box. These are more popular now. They actually look inside the model, usually at the raw activation tensors or the sequence of hidden states as the model reasons.
Like CoE or COT kinetics.
Precisely. Chain of embedding, COT kinetics. Often people train a simple linear probe, like a logistic regression classifier, on these internal states to predict if a reasoning step is correct or not.
That sounds more powerful than black box.
It definitely is more insightful. You're seeing something about the internal state. But, and this is the key limitation, it's fundamentally about correlation. These methods can find an internal state pattern that statistically correlates with errors. Maybe like, putting a stethoscope to the wall and hearing an odd rhythm.
Yeah.
But they can't pinpoint the actual causal mechanism.
They don't tell you which specific part of the machinery broke down.
Exactly. They don't identify the latent algorithm or the specific computational structure that led to the failure. It's correlation, not causation.
Which brings us neatly to this white box solution they propose.
Oh.
Circuit-based reasoning verification, or CRV.
Right. And this is where it connects directly into all the recent advances in mechanistic interpretability.
The idea of finding circuits inside models.
Yeah. The core concept builds on that foundational work. The idea is that LLMs aren't just statistical parrots. They actually execute algorithms, latent algorithms, implemented by specific subgraphs, these circuits made of attention heads and MLP layers.
Okay, so CRV takes that idea and runs with it for verification.
Precisely. The CRV hypothesis is actually quite elegant. It says a reasoning failure isn't just some noisy internal state. It's a structural flaw in how one of these latent reasoning circuits executed.
So if the algorithm execution is flawed, the structure of the execution trace itself should look different.
That's the bet. These failures should leave detectable structural fingerprints, measurable deviations from the norm on the computational graph that represents the model's step-by-step execution.
Instead of just listening with a stethoscope, we're opening up the machine and actually tracing the wiring diagram.
That's a great analogy. CRV uses the attribution graph, which aims to be a high-fidelity map of causal information flow inside the transformer as its main object of analysis. It treats that graph as the definitive execution trace.
Now that sounds computationally expensive.
Oh, it absolutely is. We'll get into that. It's more of a scientific instrument right now. But the potential payoff is huge. Getting insights that are actually causally linked to why the model failed.
So what are the key claims or findings we're going to explore from this work?
They really boil down to three main things we need to confirm. First, feasibility. Does this structural signal actually work? Can it verify reasoning steps more accurately than the black box and gray box methods, especially for structured tasks like math?
Okay, does the fingerprint exist and is it detectable?
Right. Second, domain specificity. What do these error fingerprints look like across different types of reasoning? Is an arithmetic error structurally the same as a logical error, or are they distinct?
Interesting. So how generalizable is this structural signal?
Exactly. And finally, the really exciting part, causality. If CRV finds these structural signatures, are they actually causing the errors? Can we prove it? And crucially, can we use that knowledge to intervene and maybe even correct the reasoning?
Ah, so moving from just diagnosing the problem to potentially prescribing a fix.
That's the ultimate goal here, moving from passive diagnosis to active intervention. It's a really ambitious agenda.
Okay, sounds like we have our work cut out for us. Let's start by laying the groundwork. How do you even begin to make the model's computation legible enough to find these fingerprints?
Right, that's step one. Before you can analyze the structure of failure, you need tooling to actually see the computation in an interpretable way. And that starts with defining these conceptual circuits and critically modifying the model architecture itself.
Modifying the model. How?
Well, if you're familiar with mechanistic interpretability, you know the concept of a circuit, this specialized subgraph, doing some understandable job, like addition or detecting previous failures. CRV assumes that a correct execution of, say, an arithmetic circuit will create a different attribution graph structure than a faulty one.
Makes sense. But standard transformers have those dense MLP layers, right? They're notoriously hard to interpret.
Exactly. That's the bottleneck. The standard MLP blocks output these dense, high-dimensional vectors. They're not sparse, and it's incredibly hard to say, this part of the vector means addition, and that part means multiplication. It's all tangled up.
So how do you untangle it?
This is where a really powerful tool comes in, transcoders. They are absolutely essential for CRV. They are used to create interpretable features by actually replacing the standard MLP blocks in the model.
Replacing them entirely.
Yes. Specifically, they use what they call per-layer transcoders, or PLTs. Think of a PLT as a specialized kind of sparse autoencoder, an SAE. But instead of just reconstructing its input, a PLT is trained to mimic the entire input-output function of the MLP block it's replacing.
Okay, so it takes the input that would have gone to the MLP.
Right, the residual stream before the MLP.
And it has to produce the output that the MLP would have produced.
The residual stream after the MLP.
But it has to do this through a bottleneck.
Exactly. A sparse, interpretable bottleneck. That's the key. The transcoder has this intermediate layer with a huge number of potential features, but it's forced to only activate a small number of them at any given time.
How huge are we talking?
In this work, they use the Llama 3.18b instruct model. Its normal MLP hidden dimension is 4096. The transcoder's latent feature dimension, a massive 131,072 features.
Wow. Why so many?
That huge, overcomplete dictionary is intentional. It comes from the SAE research. The hypothesis is that if you give the model a vast number of potential concepts or features to choose from and force it to be sparse, it's more likely to learn features that are monosemantic.
Meaning each feature represents just one single clean concept.
Ideally, yes, like one feature for addition, another for identifying the subject of the sentence, and so on. If the dictionary is too small, features tend to become polysemantic. They mix unrelated concepts, making interpretation impossible.
And the sparsity forces it to choose just a few relevant concepts for each step.
Precisely. They used a top K activation function, so even though there are over 130,000 possible features, only the top K 100 and 200 and $208 strongest activations actually get passed through in the forward pass for each token.
It's a massive dictionary, but only a tiny fraction is active at any moment.
Right. It forces the computation to flow through this sparse, hopefully meaningful set of learned features. These transcoders were trained on a huge data set, 10 billion tokens from Red Pajama v2 using a standard L2 reconstruction loss to make sure they accurately mimicked the original MLPs, while the top K function ensured sparsity.
So without swapping out the MLPs for these sparse transcoders, getting a clean, interpretable computational graph would be basically impossible.
Pretty much. This architectural modification is foundational. It makes the intermediate computations legible, allowing the construction of a sparse, meaningful attribution graph later on.
Okay, so we have an interpretable model now. How do we formally set up the verification problem itself?
So the goal is, for any given reasoning step in the chain of thought, let's call it silly steps, we want to predict if it's correct or incorrect. The CRV pipeline does this in stages. First, you generate the step using the transcoder model. Then you construct its attribution graph, let's call it add $.
It's structural fingerprint we talked about.
Well, not quite yet. $. is the raw material. From that graph, idiot graph, you then extract a feature vector, $6. This vector, $6 reverse, is the structural fingerprint. It's a fixed size vector summarizing the graph's properties.
Got it. And then you train a classifier on these fingerprints.
Exactly. You train a diagnostic classifier to take that structural fingerprint, $6, and predict the step's correctness, which is either correct or incorrect.
But this whole process requires incredibly detailed data, right? You can't just use standard text data sets.
Absolutely critical point. Standard data sets like PRM 800K, which just have the text of the code T and maybe a final answer label, are completely useless for CRV. You need the full computational trace, all the activations, the attribution graph structure for every single step.
So they had to create entirely new data sets.
They did. They curated custom data sets specifically for this, containing tuples of text prompt, step generation, step label, and the full computational trace. They focused on two main categories.
Which were?
First, synthetic data sets. These were multi-step arithmetic problems and Boolean logic problems.
Nice synthetic.
Control and clarity. These tasks are intrinsically compositional, meaning they build up step by step. And crucially, the ground truth for whether a step is correct or not can be checked programmatically. There's no ambiguity.
So you know for sure if step 3 was mathematically correct.
Exactly. And they could systematically control the difficulty by changing the number of operators in the expressions. They use sets with 5, 7, and 10 operators. This lets you test how robust the structural signals are as the problems get harder.
Okay, synthetic gives you clean ground truth. But what about real-world messiness?
For that, they used GSM-8K. That's the standard benchmark for grade school math problems. These involve natural language understanding and calculation, making step-level verification much trickier.
How did they handle labeling the steps in GSM-8K then? That seems subjective sometimes.
It required a very careful, multi-stage process to ensure label quality, which is vital for finding subtle structural signals. They used a semi-automated approach. A much stronger LLM Llama 3.370B instruct acted as an initial expert judge.
Using a bigger model to judge the smaller one.
Right. It checked each step for arithmetic and logical consistency with the preceding steps. But they didn't just trust the LLM judge blindly. A significant subset of these judgments was then manually reviewed by humans to validate the process and ensure high-fidelity labels.
That sounds thorough. Essential, really, if you're looking for subtle structural flaws.
Absolutely. Garbage in, garbage out applies especially here. You need pristine labels to train a sensitive structural detector.
This focus on label quality brings up a really tricky issue in COTO verification. Error propagation. What do you do if the model makes a mistake in step 3, but then step 4 is a perfectly correct calculation based on that wrong number from step 3?
Ah, yes. That's a fundamental challenge. Is step 4 corrupt because the math is right, or incorrect because it's operating on faulty premises? Labeling that is a nightmare.
So how did they resolve this?
They adopted a very clear and strict truncation policy. And this is arguably a cornerstone of the methodology that makes the CRV results interpretable.
What's the policy?
Simple, but effective. Once a reasoning path gets corrupted by an error, everything that follows is considered contaminated. So they only keep the reasoning steps up to and including the very first incorrect step.
Everything after the first mistake gets thrown out.
Exactly. Even if a later step looks like a valid calculation in isolation, it's discarded from the training and testing data because it stems from a corrupted state.
Okay, that makes a lot of sense. It forces the classifier to focus purely on identifying the origin of the failure, the exact point where the computational integrity first broke down.
Precisely. It avoids the ambiguity of trying to classify correct math on wrong numbers. It keeps the target signal clean, find the structural signature of that initial breakdown. This clean signal is what allows the white box approach to really shine.
All right, so we have the interpretable model using transcoders, and we have these carefully curated data sets with the truncation policy. Let's walk through the actual CRV pipeline now. How do they get from a reasoning step to that structural fingerprint vector?
Okay, so it's a 4-stage process. Stage 1 was getting the interpretable model with transcoders, which we've covered.
Wow.
Stage 2 is attribution graph construction. This is where they actually trace the causal flow of information for a given reasoning step, $60.
How do they build this graph?
They use a greedy pathfinding algorithm. It's adapted from prior work in mechanistic interpretability. Essentially, it starts from the final output logits for the token being generated in that step.
Like the probability distribution over the next word or number?
Exactly, and it works backward through the layers, tracing the connections that had the highest attribution or influence on those final logits. It's trying to identify which upstream neurons, which specific transcoder features, and which input tokens were most causally responsible for producing that output token.
And the result is a graph, T-dollar.
Yes, the output is a graph $2 equals VE that represents this causal flow. It's designed to be sparse, the edges are weighted, representing influence strength, and it's directed, showing the flow of information.
What are the nodes and edges in this graph?
The nodes, $5, are basically the key computational components involved. This includes the input tokens, so the original prompt, and any previous steps in the covert. It also includes all the active transcoder features, those 128 sparse features that fired in each layer during that step's computation, and finally the output logits themselves.
And the edges.
The edges, EBI, represent the strength of the causal link. A heavy edge from, say, feature X in layer 10 to feature Y in layer 15 might mean that activating feature X strongly influenced the activation of feature Y. And ultimately, these paths lead to the final logits, explaining why the model chose, say, the digit 7 as the next token.
Now, you mentioned they computed attribution after the step was generated. Was that important?
Yes, they tested computing it before generating the token versus after. They found empirically that using the state after the final token of the step was generated, the after setting consistently gave a better, stronger signal for verification.
Why might that be?
It's likely because the full computational process, including any potential breakdown during the final token selection, is fully captured in the state after the token is produced. Computing it before might miss errors that occur right at the end of the step. So the after setting provides the most complete picture of that step's execution.
Okay, so we have the attribution graph, DLers. Now, stage 3, extracting the fixed size feature vector, $6 the actual structural fingerprint. You mentioned pruning first.
Yes, pruning is crucial. The raw attribution graph can still be quite complex. To focus on the most important parts, they prune it, keeping only the nodes and edges that account for the top 80% of the total influence flowing towards the final logits.
So you concentrate on the dominant causal pathways.
Exactly. It improves the signal-to-noise ratio for the classifier. Then, from this prune subgraph, they extract the feature vector $6. This vector is carefully designed, grouping features into 3 distinct families that capture different aspects of the graph's structure.
Okay, let's break down these families. What's the first one?
The first family is global graph statistics. Think of these as the coarse, high-level measures of the pruned graph.
Like what?
It includes things like the total count of active transcoder feature nodes remaining after pruning. A very low count might suggest the computation was unusually sparse or maybe fragmented.
A sign of breakdown, perhaps?
Potentially. They also include some standard black box features here, like the final logit probability of the top token and the entropy of the output distribution. These are integrated partly for comparison, but also because they provide a basic summary of the model's confidence related to the influential subgraph.
Okay, so global stats give a rough overview. What's the second family?
This gets more mechanistic. Node influence and activation statistics. Here we're digging into the dynamics of the interpretable transcoder features themselves.
Analyzing the concepts that fired.
Precisely. How strongly did they fire? How much influence did they have? So this includes statistics mean max, standard deviation calculated over the actual activation values of the active transcoder features.
What could that tell you?
Well, for instance, a very high standard deviation might mean a few features fired extremely strongly while others were quiet. Perhaps the model relied too heavily on one specific feature, which might have been the wrong one. Even more critical are the influence scores. They quantify how much of the final output decision can be attributed back to these learned transcoder features versus how much came from the residual stream, the sort of default pathway, or from nodes that couldn't be decomposed into features.
Why is that important?
If a large chunk of the influence bypassed the interpretable features and came directly from the residual stream, it might suggest the specialized circuits weren't properly engaged. Maybe the model defaulted to a less precise computation, indicating an error or an incomplete algorithm execution.
And they also look at layers.
Yes, they include a layer-wise feature histogram. This shows the distribution of active features across the model's layers. The idea is to see if errors tend to involve features concentrated in early layers, maybe misunderstanding the input, or late layers, corrupting the final calculation. It characterizes the computational depth of the active features.
Fascinating. Okay, third family. Sounds like it's about the connections.
It is topological and path-based features. This family analyzes the actual structure of the information flow within the prune graph. Is the wiring itself sound?
What kind of topological features?
Basic graph metrics like graph density, how interconnected is the graph. Also, statistics on the edge, weights their sum, mean, standard deviation. The hypothesis here is quite intuitive. A structurally sound computation might have a dense, strongly connected graph, while a failure might result in a sparse, fragmented graph where key information pathways are weak or missing.
Makes sense. What else?
They look at centrality measures, things like degree centrality, how many connections a node has, and weighted between kilomiss centrality, how often a node lies on the shortest paths between other nodes.
Identifying the computational hubs.
Exactly. If a node that normally isn't central suddenly becomes highly influential, or if a normally critical hub is bypassed, that could indicate an abnormal, possibly incorrect, computational flow.
And you mentioned path lengths earlier. That seemed crucial.
Extremely crucial, especially for checking if the model is using the context correctly. They measure the shortest path length from the input token nodes, representing the prompt in prior context, to the final output logit nodes.
What does a short or long path mean?
A short path suggests efficient propagation of context. An abnormally long path might mean the computation took a very roundabout route to connect input instructions to the output step, perhaps indicating confusion. But the most damning signal is if the shortest path doesn't exist at all.
Meaning there's no connection.
Right. It implies the influential parts of the graph leading to the output are completely disconnected from the nodes representing the input instructions or the previous reasoning step. It's a strong structural signal that the model is effectively ignoring its context when generating the current step. This directly probes whether the model is attending to and using the relevant information.
Wow. Okay, so that feature vector $6 is incredibly rich. It captures global structure, local feature dynamics, and the topology of information flow. Now, stage 4, you need a classifier that can handle this complex, mixed bag of features.
Right. This isn't like image data where you can throw a standard CNN at it. It's heterogeneous, tabular data counts, memes, densities, path lengths. They needed something robust for this.
And they chose a gradient boosting classifier, a GBC.
Yes, GBC, specifically using implementations like XGBoost or LightGBM, is a very strong choice for this kind of data. Gradient boosting models are excellent at finding complex, nonlinear patterns in tabular feature sets with mixed data types.
And importantly for this work, they give you feature importances.
Absolutely critical, because the goal isn't just prediction, it's understanding why the prediction was made. Tree-based ensembles like GBC provide robust measures of feature importance, showing which of those structural features, graph density, mean activation, path length, etc., were most influential in the classifier's decision. This is essential for the later steps of mechanistic analysis and causal intervention.
Did they compare GBC to other classifiers?
They did. Their ablation studies showed GBC gave a consistently strong performance profile. Interestingly, a simple logistic regression model was surprisingly competitive on some tasks.
Really? Logistic regression?
Yeah, which suggests that even though there are complex interactions captured by the GBC, the structural features are often informative enough that even a linear boundary can achieve decent separation in some cases. But for the best overall precision and robustness, especially for capturing those computational near misses, the GBC ensemble was superior at learning that complex boundary-defining computational integrity.
Okay, the whole pipeline is laid out now. Interpretable model, curated data, graph construction, feature extraction, and the GBC classifier. Let's get to the results. RQ1. Does this whole elaborate process actually work better than the simpler methods?
This is the first major empirical test, and the results are, well, quite striking. The answer is a resounding yes. CRV, using these structural fingerprints, significantly and consistently outperformed all the baselines they tested against.
That includes the black box ones like MaxProb and Energy, and the gray box ones like CoE and the linear probe on hidden states.
Yes, across the board on all datasets, synthetic arithmetic, Boolean, GSM-8K, and using standard verification metrics like AURC and AUPR.
Let's see, some numbers. How big was the improvement, say, on the clean arithmetic task?
On synthetic arithmetic, CRV hit an AURC area under the ROC curve, a measure of overall discriminative ability of 92.47.
Okay, that sounds high. How did the best baseline do?
The strongest baseline on that task was the energy score, a black box method. Its AROC was only 76.45.
Wow, that's nearly a 16-point difference in AROC.
Oh,
That's huge in this field.
it's a massive leap. It strongly confirms the core hypothesis. When the reasoning task is highly structured and algorithmic, like arithmetic, the difference between a correct and incorrect execution leaves a very clear, statistically detectable structural fingerprint in the computation trace. Valid solutions seem to induce highly consistent execution paths.
OROC gives the overall picture. But for practical use, you care about reliability, right? Avoiding false alarms. How did it do on metrics like false positive rate?
Exactly. They looked closely at FPR, at 95, the false positive rate, when your system is set to catch 95% of all the real errors. So 95% true positive rate or recall. You want this FPR number to be as low as possible.
What did they find?
On that same arithmetic task, CRV achieved an FPR at 95 of 37.09%.
Meaning less than 38% of the steps it flagged as errors, while catching 95% of true errors were actually correct steps.
Yeah.
Okay, how does that compare?
The best gray box baseline, the LR probe on hidden states, had an FPR at 95 of 63.33% on the same task.
Over 63%. So to catch most errors, the baseline would flag nearly 2/3 of its alerts incorrectly.
Pretty much. That's often an unacceptably high false alarm rate for practical applications. CRV cuts that false positive rate almost in half in this case. It shows the structural signal isn't just detectable, it's reliable and leads to much higher precision in the diagnosis.
Okay, so CRV nails it on structured tasks. But that leads right into the next question.
Yeah.
How well does this knowledge transfer? If you train a CRV classifier to spot arithmetic errors, can it also spot errors in, say, GSM-8K math problems or Boolean logic? Or are these fingerprints specific to the domain?
This cross-domain generalization analysis yielded one of the most scientifically interesting findings, I think. It really highlights both the richness of the signal CRV captures and, perhaps, its current limitations.
What happened when they tried to generalize?
When they took a CRV classifier trained on one domain, like synthetic arithmetic, and applied it directly zero-shot to a different domain, like GSM-8K or Boolean logic, the performance plummeted.
How badly?
Often the performance drops so much that the sophisticated CRV classifier performed worse than even the simple training-free baselines like MaxProb on the new domain.
So the structural signature of, say, messing up multiplication is fundamentally different from the signature of misunderstanding a word problem in GSM-8K.
That appears to be the case. The results strongly suggest that these error fingerprints are highly domain-specific. The structural patterns associated with failures in formal logic seem distinct from those in precise arithmetic calculation, which are again distinct from failures in reasoning that involve language understanding and parsing complex conditions.
That's fascinating. It implies you might need specialized verifiers for different kinds of reasoning.
Exactly. It's not necessarily a failure of the CRV approach, but rather an indication of the complexity and specialization within the LLM's own reasoning processes. It suggests that aiming for a single, universal error detector based on structure might be difficult. For high precision, domain-adapted structural verifiers might be necessary.
Okay, so limited generalization across domains.
Yeah.
But what about within a domain? Does the signal hold up as problems get harder? They tested this with the synthetic arithmetic, right? Increasing the number of operators.
Yes, they used the synthetic arithmetic datasets with $1 $110, $187, $109 operators to test robustness to increasing difficulty.
And did CRV maintain its edge?
It did. CRV showed a clear and consistent performance advantage over the baselines across all three difficulty levels. While accuracy might drop slightly for all methods as problems get harder, simply because errors become more likely, CRV's superior AROC and lower FPR at 95 remain stable relative to the others.
So the structural signature of correct arithmetic is robust, even when the calculations become more complex and prone to failure.
That's what the evidence suggests. The model's reasoning machinery seems to degrade in structurally predictable ways when put under increased load within a specific domain, and CRV is particularly good at detecting those predictable structural deviations.
This brings us to RQ2 and RQ3, digging deeper into what those structural signatures are and whether they're actually causal. This is where the white box approach really pays off, right?
Absolutely. We're moving beyond just saying CRV works better to understanding why it works better and what that tells us about the model's failures.
So RQ2 first. Dissecting the fingerprint. Which parts of that complex feature vector, the global stats, the node features, the topology, are most important for detecting errors?
They did a feature ablation study, specifically focusing on the arithmetic task where the signal was clearest. They systematically removed each family of features and measured the drop in performance.
And the verdict.
The results were quite clear. The family of node influence and activation features was the most critical. Removing just this family caused the biggest hit to performance. The FPR at 95 jumped by over 12 percentage points, which is a substantial degradation.
So it's less about the overall shape of the graph and more about the state of the individual interpretable features, how strongly they fired, how much influence they had.
For structured tasks like arithmetic, that seems to be the dominant signal. It suggests that errors often manifest locally, perhaps as a specific, crucial transcoder feature firing too weakly, too strongly, or being unduly influenced by the wrong inputs, rather than a complete collapse of the overall graph topology.
Does the qualitative evidence back this up? They visualized some feature distributions, right?
Yes, they did. Even for the noisier GSM-8K dataset, when they plotted the distributions of certain features like graph density, mean node influence, or the number of pruned feature nodes, they found statistically significant differences between the distributions for correct steps versus incorrect steps.
So incorrect steps tend to have, say, lower graph density on average.
Something like that, yes. The distributions were separable, statistically speaking. However, the full picture emerges when you look at dimensionality reduction plots, like TSNE projections of the entire high-dimensional feature vector.
What did those show?
Figure 3 in the paper is key here. It doesn't show two nice separate clusters for correct and incorrect steps. Instead, the incorrect steps often form a dense clump inside the larger cloud of correct steps.
Ah, the computational near misses idea again.
Exactly. Many failures are structurally quite similar to correct computations, which is why simple linear probes or global stats might struggle. The model almost got it right structurally.
But there's a distinction.
Yeah. Crucially, yes. The projection reveals what they call a zone of computational integrity. It's a specific region in this high-dimensional structural feature space defined by particular combinations of node activations, influence scores, path lengths, density, etc., that seems to be occupied only by correct reasoning steps.
So CRV works by learning the complex boundary around this safe zone.
Precisely. It's learning the complex, nonlinear definition of what structural properties must hold for a computation to be considered sound within that domain. Incorrect steps fall outside this zone, even if they look superficially similar in some dimensions.
This detailed structural understanding is what enables RQ3, the causal interventions. Because you don't just know that a step is likely wrong, you know which structural features make it look wrong.
Exactly. This is the unique power of the white box approach combined with interpretable features. The features that the GBC classifier flags as highly predictive of error can often be traced back to specific components in the model, particular transcoder features in specific layers. And because you can identify them, you can try to manipulate them.
You can surgically intervene in the model's forward pass.
Right. This allows for testing causality directly. If manipulating a feature that CRV flags as error-like actually changes the model's subsequent behavior, ideally correcting the error, then you have strong evidence that the feature's state was causally involved in the failure.
And they have case studies demonstrating this.
They have two really compelling ones that act as powerful proof of concept for this closed-loop diagnosis and correction.
Okay, walk us through case study 1. Suppressing a feature that fired wrongly. What was the error?
The task was a synthetic arithmetic problem. 7 helm, 5 plus 9 plus 7 times. The model started correctly, calculating $5 plus 9, 14.6x.
Okay.
But on the very next step, it made an order of operations error. Instead of calculating $14 plus 700 inside the parentheses, it jumped ahead and calculated $13, $980. It performed the outer multiplication prematurely.
How did CRV diagnose this?
CRV flagged that second step, 714, 900, as incorrect. And when they looked at the feature importance analysis from the CRV classifier for that specific step, it pointed to an unusually high activation value for a specific transcoder feature in a late layer feature, ID 91812. Further analysis suggested this feature was strongly associated with the concept of multiplication.
So the diagnosis was a multiplication feature fired too strongly, too early, overriding the correct order of operations.
That was the hypothesis based on the CRV structural fingerprint, so they performed an intervention.
What did they do?
They reran the generation of up to the point right before the error. Then, using a forward hook, a targeted code injection during the forward pass, they manually forced the activation value of only that specific feature, ID 91812, to 0 for that step.
They just silenced the faulty multiplication impulse.
Exactly, they surgically suppressed it.
And the result, did it fix the error?
It did. With that single feature's activation clamped to 0, the model no longer had the premature multiplication impulse. It correctly generated the next intended step. $14 plus 7, $201. And from there, it proceeded correctly to the final answer. $721, $140.47, $7. Fixing that one feature's activation based on the CRV diagnosis put the entire computation back on the correct path.
That's incredible. It's like debugging the model's thought process directly. Okay, what about case study 2? Amplifying a feature that was underactive.
Case study 2 involved a different kind of error, this time interpreting a unary minus sign in the expression 1 and a 5 plus $49.
Okay, what did the model do wrong?
It correctly calculated the inside part, $49, $36, $7, and then $5 plus $36, $4, and $1. So far, so good. But then faced with $1 and $1, instead of interpreting the unary minus as multiplication by 9 of 1 to get 9 of 2, 1.
What did it do?
It seemed to interpret it as subtracting 41 from an implicit 9 of 1, incorrectly generating the step 1 9 of 4, 9 of 1, 9 if everyone's related to 42, 2.
How did CRV explain this failure?
The CRV analysis of the structural fingerprint for this failed step suggested the problem was the absence of a strong enough signal related to multiplication. The necessary circuit or feature for multiply by -1 seemed to be underactivated or didn't have enough influence.
So the intervention was the opposite of the first case. Instead of suppressing a feature, they needed to boost one.
Exactly. They identified a different transcoder feature semantically linked to multiplication. Then, they reran the generation to the point of error and used a forward hook to manually increase or amplify the activation value of that specific feature.
Trying to nudge the computation towards the correct interpretation.
Precisely. And again, it worked. By boosting the relevant multiplication signal, they steered the model away from the incorrect subtraction interpretation and onto the correct path. It successfully generated the step leading to the correct final answer, -41.
So both suppressing an overly active feature and amplifying an underactive one, guided by the CRV structural diagnosis, demonstrably fixed the reasoning errors in these cases.
Yes. These interventions provide really strong closed-loop evidence establishing the causal role of these structural signatures. The features CRV identifies aren't just correlated with errors, they are, at least in these cases, directly involved in causing them. This is a major step beyond correlation-based verification.
Absolutely. Okay, let's wrap up by putting CRV in context and discussing its limitations and where this might lead. How does it relate to other work, like process reward models?
Good question. Process reward models, or PRMs, like the ones developed by Lightman and others, also evaluate COT reasoning step by step, but they typically work differently.
Oh, so?
PRMs usually train a model, often another LM, to predict the correctness or quality of a step based on its textual content or maybe its hidden state representation from the original model.
Whereas CRV ignores the text and hidden states.
Largely yes, except for integrating some basic black box features derived from logits. CRV's core analysis is purely on the structural properties of the computation graph derived via attribution through the interpretable transcoder features. It's a fundamentally different lens.
And it builds directly on mechanistic interpretability tools.
Absolutely. It takes concepts like sparse autoencoders, SAEs, transcoders, and attribution methods, which were often used for qualitative analysis like, let's look and see if the circuit looks right, and operationalizes them. CRV turns them into a system for automated quantitative verification based on learned structural norms. It's moving interpretability from observation to application.
It sounds incredibly powerful, but the authors are also upfront about the current limitations, right?
Yes, and that's important for understanding its current place. The most significant limitation, as we touched on earlier, is computational intensity.
It's just too slow and resource-heavy for real-time use.
Right now, yes. Training the transcoders takes significant compute. Replacing the MLPs adds overhead. And crucially, constructing that detailed attribution graph for every single reasoning step is very expensive. It's firmly in the realm of a scientific instrument for deep analysis, not a scalable, production-ready verifier.
What other limitations did they acknowledge?
Generalizability is another key one. As we saw, the error signatures seem highly model-specific. They were found on Llama 3.18b with specific transcoders. We don't know yet if these exact fingerprints apply to other architectures, like mixture of experts models or different model sizes.
And the domain specificity we discussed.
Exactly. The fact that arithmetic errors look structurally different from logic errors means you likely need domain-specific training data and classifiers, limiting the dream of a single universal structural verifier, at least for now.
And there's a limitation related to how the classifier itself works.
Yes, the aggregative analysis. The GBC classifier, powerful as it is, operates on statistical summaries of the graph counts of nodes, means of activations, graph density, average path lengths. It's learning correlations between these aggregate statistics and correctness.
It's not reasoning symbolically about the features.
Correct. It doesn't understand the semantics of transcoder feature 9181 free representing multiplication. It just learns that if feature 9181's activation is statistically unusual in a certain context, like being too high in the arithmetic case, that pattern correlates with errors. It can't perform a check like, is the addition feature active and is it being influenced primarily by numerical inputs from the previous step?
It's statistical pattern matching on structure, not symbolic reasoning about the circuit's logic.
Precisely. It's learning the boundary of the zone of computational integrity, statistically, not by verifying logical rules about feature activation.
Okay, so summarizing the core insight here.
I think the central takeaway is that the way an LLM computes the actual flow of information through its latent circuits leaves behind a structural trace, and critically correct reasoning and faulty reasoning create measurably distinct structural fingerprints on that trace. CRV demonstrates that these fingerprints are verifiable and, importantly, provide a causal handle on understanding why failures occur.
Which is a huge step beyond just knowing the model is uncertain or its internal state looks weird. We're getting closer to diagnosing the specific algorithmic breakdown.
Exactly. It elevates the discussion from correlation to causation, from observing symptoms to understanding the underlying mechanism of failure.
So looking forward, that last limitation you mentioned, the aggregative statistical nature of the current classifier, seems to point towards a really exciting future direction.
I agree. The fact that CRV works so well, even relying only on these statistical aggregates of graph structure, is incredibly promising. It proves the signal is definitely there in the structure.
Which leads to the provocative final thought. What happens next? If the statistical approach works this well, what could we achieve if we moved beyond statistics?
This really motivates the push towards developing a new kind of verifier, a truly neurosymbolic verifier.
Meaning?
Imagine, instead of a GBC learning a complex statistical boundary based on feature averages and graph density, we build systems that operate directly on the semantics of those thousands of disentangled transcoder features.
So you'd have rules or checks based on what the features actually mean.
Potentially, yes. If we can reliably map features to concepts like addition, negation, entity recognition, etc., maybe we can build formal logical checks. For instance, if the input requires addition, is the addition feature active? Is it receiving input primarily from nodes representing numbers? Is its influence appropriate for this stage of computation?
Moving from statistical correlation on graph properties to something closer to formal verification operating on the learned concepts within the network.
That's the vision. It's a huge leap, requiring much better feature interpretation and linking structure to symbolic meaning. But if we could achieve that, moving from statistical checks on graphs to logical checks on circuit semantics, that could represent a major breakthrough in ensuring the fidelity and reliability of LLM reasoning.
A fascinating direction indeed. Building verifiers that understand the model's own learned language of concepts.
It's a crucial frontier for making AI systems more trustworthy and understandable. Thanks for digging into the computational graph with me today.
Always a pleasure. Thanks for joining us on the Deep Dive.